Good morning. This is the last day of regular class. We'll meet again next Monday. And I did get some exams back, and I'm just going to talk about one issue that both of you made. And now I'm documenting it on the video for all time's sake, since I don't know if I'll ever teach this class again. So we will finish up on information theory, but one of the misunderstandings, and it's an easy misunderstanding, since you both made it, let me just say what the scores were. I mean, the scores on exam 1, for, I'll just say last name, since that's where I have my sheet set up, for Lotfi and Shaker, the scores were like 91, 95, and then for exam number 2, 97, 93. So pretty similar, and actually differences, and like one did better than the other, but you know, it's just little things. And then, but a fundamental mistake has to do with QPSK. And both of you thought that QPSK was 3 dB worse than BPSK, when it's not. It's actually identical in terms of the bit error probability, which would be the serial bit rate, because normally when you demodulate BPS or QPSK, you're going after the in phase and the quadrature. This curve right here shows, in terms of symbol error probability, that there's a difference. But this curve is also misleading because it has energy per symbol and energy per bit comparison. But when you go through the serial portion, and I'm not sure I actually have the best picture in here. I guess I probably don't, but it seems like there was a summary over here.
Wasn't that the discussion where you had to divide by log 2m, right?
Yeah, but we're not looking at symbol error probability in the end. We're looking at bit error probability. So it turns out that this is, this was a bound, but if we were to go in and look inside, I guess I'll just pick a constellation for MPSK, and we look at it in terms of energy per bit, not energy per symbol. We have 4 different locations we can be in for QPSK, right? So if we make our bit detections on the in phase, we have a threshold detector, and we detect whether it's on the positive or negative real axis. And then for the quadrature, we do the same thing. And I'm now rotating the whole thing by 90 degrees or 45 degrees so that it's actually, in this, my other graduate student said, why is QPSK always shown with the 4 points like this rather than rotated? And actually, when you demodulate QPSK, you actually demodulate it with it rotated, because you want to have it be such that you're simply looking at the real part, deciding the sign of the real part, and then you're looking at the sign of the imaginary part, which gives you the 2 points. So the energy per bit that you have to put into the system is the same, and you get the same error probability. What makes QPSK not as desirable as BPSK, though, is if there is a phase error, then there's a slight rotation, and you project. You get crosstalk, because you get some of the quadrature will project onto the real axes and vice versa. So you have more complexity. You have to maintain the phase imbalance, and of course amplitude imbalance goes along with that, but the phase imbalance would be where you're not perfectly in quadrature. So that is an impact, but other than that, the serial bit error probability is the same. Now, I could argue further, but I guess you can go look in the solutions and stuff that was written out for, it was a homework problem, and I don't remember the number though, but there was a problem on that. It's not like I'm chastising you, I'm just wanting to make sure you don't have that misunderstanding going forward when you talk about it.
Yeah, I remember it was on homework 5.
But when you answered the one question on the exam, it was, what are the pros and the cons? You both had a con of QPSK as being 3 dB more, but that's not true. But it is more complicated. It's more sensitive to the phase imbalances. So you can think about it, but that's what it is. And it's one of the fundamental things, which is why Dr. Zemer has that question in there. We're interested in the serial bit error probability, and that's what makes QPSK pretty nice, because you can demodulate it in phase to get the, say, the even bits, and then the quadrature gets you the odd bits, and then you're immediately demultiplexed into two. The two streams come back together then as a serial stream, even and odd bits, and they're the same as BPSK. And you're both correct in that its bandwidth efficiency is double that. So that's good. Other than that, everything came out okay. There were little things, little confusion points, and I tried to write notes on the papers. What I want to do now, unless you've got a question about that, is I want to go into the information theory chapter, because this is going to be a sweeping day of information theory and coding. But it's not particularly hard unless you want to mess around with the details. So the next chapter is...
You said you're sending back the exams on Slack, right?
Yeah.
So I can just ask you questions on Slack.
Yeah, it should be on Slack right now.
There's nothing at task since I haven't seen it.
Yeah, it's on Slack. So if you looked on your phones, you'd see that it's there.
Okay.
Actually, I'll just prove it to myself, because I sent it from my tablet, which is on the wireless. And I'll just look at Slack, since I'm waiting for my wife to write back to me. I'll just pick one of you. Yep, they're there. And Shaker, they're there. So they're both there. Okay, information theory and coding. This is, obviously it's really hard to stop what we were doing in the other chapter, because that just goes on and on and on. Likewise, this topic, information theory and coding, is just huge. I mean, I was looking at some things yesterday, trying to enhance the notes ever so slightly and fix some minor bugs, and I just went looking on IEEE Explorer, and both of you use IEEE Explorer, I'm sure, at least once, twice, maybe dozens of times by now. I don't know. I use it a lot. You know what I'm talking about, IEEE Explorer in the library?
We have free accounts with work. Yeah,
okay.
So I'll check on there sometimes. When
We have it free here. I mean, for me, it's one of my benefits that I get when I retire is I have access to the library for the rest of my life, if that means anything. And what it means to me mostly is IEEE Explorer, if I want to get access to journals and stuff. So it's pretty important. We used to have another really nice search engine that I liked an awful lot. It was called Engineering Village, and I fought for it. They were cutting back on the library's budget. I used it. I encouraged my students to use it. It's a more powerful search engine, and it handles more than just the IEEE. It handles everything in Europe, IEEE, Japan. I mean, everything around the world was on Engineering Village. And Engineering Village would also search really well for holdings in our library so you could get the downloads. But it was a very expensive service, and our library decided to get rid of it. Faculty members, by and large, said they could get by without it. I was one of only a couple. I mean, the fact of the matter is, though, IEEE is not the only thing that publishes good articles that we need to go read. But we can manually get them and then try to figure out where to get them from. Because IEEE actually catalogs a few other things, too. Usually, though, I would use Engineering Village. It would find me where the papers where I wanted. I could get the abstracts, and then it would give me links to where I could go pull them from. But if they were IEEE papers, which probably 90% of them were, I just would go to I would go to IEEE Explorer and just get them there directly. But I would use the front end. As a front end, I would use Engineering Village. But you'll never see it, because if you never, did either of you ever try Engineering Village? Because I think it's only been a little over a year. Okay, you might have had it in Iran too, I don't know, because it's an international thing, but yeah. Okay, so information theory and coding. This is mostly, the founder of information theory is Claude Shannon, who published papers in the late 1940s on information theory, and he's just really, really well known as like the father of information theory. And the whole idea is to evaluate the best communication system performance based on a given bandwidth and a given signal-to-noise ratio. So one of the things we're going to get to pretty quickly before we even start block codes or convolutional codes is some of his fundamental coding theorems, and we'll get to this bandwidth power efficiency plane, which I've talked about before, and I said we'd eventually see that, where we could see each modulation scheme with regards to the Shannon information theory bound for reliable communication. And we can see this plotted in the plane. And that is fundamentally what we've been talking about ever since the beginning in digital comms, that we work with bandwidth and signal-to-noise ratio, right? Those are the fundamental quantities that we have for the various modulation schemes. And since that was on the papers that I graded, all of you understand that perfectly well. I mean, you got the ordering and the trade-offs, but obviously there's more to it than just that. There's implementation considerations. So we don't always go with the most bandwidth efficient or the most power efficient because there's some other criteria that might be in there. I'm going to use a kind of a crude example, but it is an example. A garage door opener is a digital communications device. You press the button and it sends out a code sequence that's unique to your house. It's kind of like a key to unlock your door. Does that have to be super power efficient? Does that have to be super bandwidth efficient? I'd say no. It has to be low cost, it has to be very portable, and it has to be simple too. I mean, simple/reliable. So I don't think when the first garage door openers were created, wireless ones, that there was that much consideration due to bandwidth. It's just in an unlicensed band, and they want the battery to last pretty long, but you're pretty close to the receiver, so you don't really have a problem with that usually either. I don't know. I use it all the time when I'm driving, and I'll have to admit, I mean, my wife has a newer car that has the built-in transmitter for the garage door. It's universal, whatever. Hers, I can press the button on it, and it gets the garage door starting to go up long before you get in front of the garage door. Mine is one that's just a little portable thing that's sitting in my car, and it does not work nearly as well. So why is that? I don't know. My surmising is the antenna is better in her car, and it's probably more power. It's probably still legal, though. I mean, it'd be very easy to make one of those violate the FCC rules for, what is it, Part 13 or something like that for unlicensed devices. But I don't even know if anybody checks those out. So it's a matter of convenience then, right? Do you want to be right in front, or do you want to be a block away? I think the police would say you should be right in front before you raise and lower your garage door. Have you any of you ever even thought about that? I had a garage burglary once, so I had an issue with, I caught the burglar. I mean, I caught the intruder, but I was out in my backyard mowing my lawn, and I usually had the garage door up when I was in the backyard, and this kid came in there, and he stole some tools. He took some money out of my wallet, which happens to be sitting in my car, which was my mistake, but I caught him because I had a suspicion. That's a whole story unto itself. But when the police came and we talked about it, and I asked the officer, what should I do? He said, if you're even in your backyard, don't leave your garage door open, close it and lock it, because you're just opening the opportunity for somebody to walk in and take something. So I guess I'm just saying what I think the police would say. Don't open your door from a block away. Somebody might even try to run in. I'm just being silly about that. But on almost all other circumstances, you know, certain military, certain deep space, and other things where power or bandwidth is a consideration, maybe that's not always the driving factor. So how do we measure? We're going to learn about how we measure information theory, how to best transfer it from the source to the destination, and then ponder these coding theorems. Fundamentally, Shannon has the fundamental coding theorem that if a source has information at a rate of information less than the channel capacity, then there exists a coding procedure such that the source can be transmitted with arbitrary transmitted from source to sink with arbitrary small probability of error. That's fundamental, but it leaves one important thing out, and I'm kind of a practically minded person. It doesn't tell you exactly how to build it. It just says there exists. And I took real analysis when I was getting my doctorate from the mathematics department, so I got deeply embedded in analysis proofs and things that you do with epsilon and delta, and you use the shorthand notation, you know, the backwards E, there exists such that, blah, 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 all that kind of stuff. So I had fun with all of that, and I don't know if, Fatma, did you have a class in analysis like that from mathematics at one point? I'm just curious.
Stochastic process.
Okay.
Like this, yeah.
So you use those symbols, though, perhaps. So, and Joseph, I don't know if you ever took an analysis class.
Discrete math.
Okay, so you had proofs in there, probably. Yeah. So I always like that stuff, but mathematicians just like to write it down on the sheet of paper. There exists. So, I mean, engineers are like, what is an example of there exists, rather than just thinking that it's out there somewhere. But, you know, it's still good. I'm not saying it's bad. It's just it has some drawbacks. So, information in the context of electrical communication. If we have some event, x of j, and it has a corresponding probability, p x of j, the information associated with that event is log base a of 1 over the probability, which then becomes minus log base a of the probability. And that's the amount of information that conveyed by that event. And it just tells you that events with smaller probability have more information. It seems really fundamental, though, right? One of the things about this, if you've never seen the information theory stuff before, is it's super elegant. It's like really, really finely dressed whatever. I mean, it's just nice and beautiful mathematics that is nice, but it's not everything. I mean, I'm practical about it, but it's still pretty cool to have it. The way it's laid out, it's really nice. So generally, the base is 2 because we're talking about sending binary information. So then the unit associated with information is bit, which is short for binary unit, right? At least that's what I remember learning a long time ago. And then if you have a source that provides different events or different piece of information, then you can talk about the entropy as the average information provided by the source, and then that's the sum over all the types of information events summed from 1 to n. And for the special case of a binary source, get this start working. We can have, you know, a 0 or a 1, and then you can just write out what the entropy is. And the entropy then is this upside down u, or cap type function, which is maximizes the uncertainty or the entropy when alpha has probability 0.5, so, or when alpha is equal to 0.5, which also makes sense, right? We're getting the maximum entropy from our source if we can make the bits be equally likely. And then if you have more types, then you just end up with 1 over n as being the maximum entropy. So
What was the formula you had above for H of alpha?
yeah, actually, for the fun of it, just because I thought maybe I'd use it, I decided to just code it in here because there's a couple of examples that we're going to come to. This notebook is not on the website yet, but we'll talk about it. This is actually a notebook that was created by one of my graduate students a few years ago who wrote the block coding module for Scikit DSP-Com, which is by no means complete, but I decided to just hack this at the beginning of the notebook that he wrote when he made his delivery to me. So the next thing is talking about channels, and we can have different types of channels for sending information, and we have discrete channel model, and that's what this black diagram is, or flow diagram is. Discrete and memoryless channel would be having some input events with associated probabilities, and then at the sink end, what are we receiving? So in this case, there's 2 types of events at the input and 3 types at the output. And this is Dr. Ziemer's classical example, but I think a lot of information theory books will use something like this. So this is saying we have 3 different categories for what we receive, and the most common channel that we use is the binary symmetric channel, but this one just shows you that we could have things mapped so that we get from 2 different types of inputs, we could get 3 different types of outputs. So the way I would think of it as, from an information theory standpoint, is y1 is x1, it's a hard value. y2 is a gray value, in that we don't know whether it's a type 1 or a type 2, and then y3 is the type 2. I mean, that's sort of a typical application where we have a soft value in the middle. So we have two certain values, and then we're going to just draw another conclusion saying we don't know, and we might carry that along and then use that in coding, because that's what we're going to be talking about too, is soft decision decoding, where you don't make hard decisions right away. You try to put together a bunch of soft information and then finally make an assessment. And this is not unlike what neural networks do, I don't think, either, where you have the hidden layers and things like that, where you're just processing things and you're trying to train on something, and then eventually you're going to be able to make a decision with your network because you've trained it with a bunch of scenarios. And I'm not a neural network expert, but I have dealt with it before, so I'm just using that sort of maybe as a modern version of this. So then you can define a channel matrix, which is just the conditional probabilities to go from the input x to the output y. The most common one, like I said, would be the binary symmetric channel, or just the binary channel. So this is not the symmetric channel because the probabilities that transition from input to outputs are not symmetric, but it is an example of a binary channel. And most communication systems are binary symmetric, or can be thought of as binary symmetric, or at least symmetric, but you can use this modeling for other types of activities where you don't necessarily have equal likely probabilities. You know, x1 may occur more frequently than x2, so you can have it be asymmetric. So some more definitions are joint and conditional entropy. So conditional entropy can be defined using the marginal entropy that we had before, H of x and h of y, and then you can use conditional probabilities and joint probabilities to get the entropy of y given x and y. So these are just some variations, and then you can do some factoring on them to have the joint entropy as the conditional entropy plus a marginal entropy. And this is, I guess, near as I can tell, it's a little bit like Bayes' rule for entropy. It's not the same thing, but it's just using things from probability theory to break this down. I'm not going to dwell on that. When I was in school, actually Dr. Zemer taught an information theory and coding class for a whole semester, so I had pretty rigorous introduction to it, but I haven't really used it for much of anything. I have a thin information theory coding book that was very mathematically dense, and it was okay. I just haven't gotten that, didn't become that fond of it myself. It was okay though. My dissertation though was on multi-H CPM, and as I've said before, when we talked about CPM, continuous phase modulation, I don't think I ever said that there's a class of combining coding and modulation theory together, and that's talked about at the very end of this chapter. And that's trying to take advantages of merging modulation theory for bandwidth efficiency, and that along with information theory ideas in coding. So in search of power efficiency and bandwidth efficiency. So combine coding and modulation, just like within the community of communication systems people, there's also in networking things, and I think Dr. Semiari is doing this because I remember reading that on his dossier since I was on his review panel. What's that called again? I was on a proposal for this many years ago too with some people at Virginia Tech. It's combined modulation, physical layer and networking layer. So there's a name for it. I'm not slipping out on my mind. It's trying to optimize something in further up in the protocol stack with the physical layer.
MAC layer?
Pardon me?
MAC layer?
Yeah, it could be the MAC layer, but it could be even further up than that, where you take information and feed it back again to say do something differently. And there's a name for that. I can't think of it. It's a whole sort of a discipline within communications where you're merging things together. And that's just things that get done. I mean, I'm trying to think. A simple example of that, I think, is what we do with Wi-Fi, right? Wi-Fi starts off with trying to decide what modulation scheme to use based on the channel and the interference from the other users on the network, the other access points that are around. So it will negotiate the proper modulation scheme because it has to get a certain amount of quality assurance, and it will just reduce the throughput then to maintain high quality, but not high quality bits without too many retransmissions. So it shifts around. I mean, the highest rate is the OFDM scheme, and then the lowest rate would be like BPSK or something like that. The one that's on the exam. Remember the one we talked about last week, the basic 7-bit Barker code spreading, and that was the original Wi-Fi, and then they've gone up to the high order modulation to get more throughput. Okay, so moving forward, now we can define using information, we can define mutual information as the entropy of the source minus the conditional entropy. So it's the entropy of the source a posteriori. So it's the entropy given what we've received. So that is the mutual information. and it's always non-negative, because what is the entropy going to do when you look at it after you've received it? You're going to get some quantity that's less than the original entropy. So the channel errors and things reduce the entropy. So you're going to get a non-negative quantity, and that's the mutual information. So it's the decrease in average uncertainty of the transmitted signal when it's received. That's called the mutual information. So the channel capacity can be defined as the maximum of the mutual information. And this is just a definition. We're going to see capital C for the next few pages. Maximum value mutual information. So it's the maximum average information per symbol that can be transmitted through the channel upon each use. So if we write that out, we get, instead of the cap, we get a cup-shaped function versus the probability p. This was alpha earlier, but now it's p for the binary symmetric channel. So, which says our capacity is at its smallest when it's 0, essentially, when we have p being 0.5. So it serves as a combination of source probabilities and channel transition probabilities. So, yeah, p is not alpha, never mind. P is the transition probability through the channel. So obviously if p goes to 0.5, it says that our channel is a coin flip. We don't know reliably what is coming out the other end. So the capacity is 0 at that point. I think that makes sense, doesn't it? When the transition probability is 0.5, it says it's going to mutilate the information. Half the time it's going to be correct, half the time it will be wrong. So that makes the capacity essentially 0, because there's no reliable communication at that point.
If it flipped more than 50%, you could correct for that.
Yeah, I guess that's right. So we'll be using this idea to look at the coding theory. So yeah, this is the first theorem right here. So there's different types of coding that we want to go into. So the two main types of coding are source coding and channel coding. So source coding is where you're trying to adjust the information to be more efficient. It's like it's the idea of compression. So source coding is to match the source to the channel via some sort of data compression. And for me, the big examples of data compression that I think of are listening to music or watching streaming video. Those are examples where we're doing some sort of lossless or lossy compression in order to get more throughput through the channel. So this is an introductory example that he has in the book, and then pretty much this gets left behind, and we just have it to think about, though. So we have a binary source that has some source symbol rate, 3.5 symbols per second. Then we were going to introduce the source encoder to try to modify that through source encoding, because we're told that the channel, binary channel, has a capacity of 1 bit per symbol, and we can send through this channel at 2 symbols per second. That's the maximum symbols per second we can put through the channel. So if we take the product of the bit rate, bits per symbol, times the symbols per second, we can only get 2 bits per second, and our source is currently producing 3.5 symbols per second. So we have a mismatch in here. RS is R times the entropy in bits per second. So and that's the source information rate. So if we take and look at that, well, we're going to continue this example in a second. So the Shannon noiseless coding theorem, and this is for source coding, says that a channel and a source that generates information at a rate less than the channel capacity, it's therefore possible to code the source output in such a manner that it can be transmitted through the channel. So as long as we can do that, maintain less than capacity going in, we're going to be able to get it out reliably. No problems whatsoever. But we have to be able to do some sort of encoding at the source end. So in the system up above, we're assuming the binary source output A and B have probabilities 0.9 and 0.1 respectively, so that's what leads to the source rate being 3.5 symbols per second. And I tried to represent that over in here. So I created this plot, but then I created a function over here for entropy. So I just have my entropy function. I can put the 0.9 in there, and then I can take it times the symbol rate of the source, 3.5. So I can get the information rate to be 1.64 when I multiply those two together, and that's what we're talking about right here. That's what this number is right here. I just thought maybe I'd do something with it, but I actually have the math written out here. So that's the 1.642 bits per second that, taking into account the entropy and the bit rate, we know that we only need to have a channel that can support 1.642 bits per second. Our channel supports 2. It does not support 3.5, but we know from the entropy of the source that it's only 0.469. So we should be able to encode it because we have 2 bits per second available on the channel. So how do we do that? We know that we can get there, and that's what Shannon's theorem says. If we're less than the channel capacity, we can do it. It doesn't tell us how to do it, but it tells us that we can do it.
So you're saying, right, that the symbol rate is faster, but the information rate isn't. So we should be able to encode it in a way to increase the entropy and lower the symbol rate.
Exactly.
Or like, yeah, have less symbols with more entropy.
Yeah. Because right now we're only at 0.47, whatever it says here, right? We're at 0.469 is the entropy, and it's ticking away at 3.5 symbols per second, but that only means we need 1.642 bits per second.
I suppose it's like what zip files do and so on.
Compression?
Yeah.
I think so. I never really think about that. I mean, I do think about it, but I don't think about it every day because I don't think about information theory all the time. But I think it kind of is in our minds as making sense, and this is a formalization of it. You know, information theory, like I said, is very, very elegant. It's got everything nicely laid out, simple quantities, simple units, and there exists part of it also is very nice too. If you're a mathematician, it's like, I'm happy because there exists and I'm meeting my requirements, so I don't have to worry about exactly the implementation right now. But there are different types, and the book does talk about them. The simplest one is what's called source extension, order n source extension. So I was reviewing this again over the weekend because I haven't had to deal with this, but there is one homework problem that kind of deals with matching things out. It's a speech coder, and I guess I should look at it so I can tell you which problem is kind of using these ideas, if you haven't bumped into it yet.
Oh, this is like Huffman coding, I think.
Yeah. Well, Huffman coding is more sophisticated than this, but it is a similar idea. So the problem I'm thinking of is problem 1211, and it gives you an exponential PDF, and it says the signal is to be quantized using 4 quantization levels, and your job is to set those quantization levels, but the idea is to maximize the entropy of the quantized amplitudes. So it's just playing around with that so you can get equally likely probabilities into each of the quantization levels with the exponential PDF. It's not exactly this problem, but it is thinking about entropy. So here, the third order extension idea just says we're going to look at possible source symbols for the case of n is equal to 3. So the case of n is equal to 3, you're going to look at all the combinations of 3 symbols from the source. So at one extreme we have 3 A's in a row, and at the other extreme 3 B's in a row. So he's going to say 3 A's in a row gets encoded as a single 0, and then assuming that they're independent, we can look at the symbol probability then as the product of 0.9 times 0.9 times 0.9, and that's 0.729. And then L sub I is the length of that particular code word. It's 1, so the in contributing to the entropy then would be 1 times the 0.729, and then just take them one at a time. AAB, the product of those probabilities, and that code word is going to be 100. And this is the assignment that's just made here arbitrarily to make sense, and then just continue on down the line with your creating code words that match the different symbol combinations, not repeating anything, of course, and then getting the weighting from the length and then summing that up and then getting the average word length. So for this particular short table, this just shows you some variations on it as you step n from 1 to 3. So initially at 1, we had no reduction in bit rate, but then as we go up to the level 3, we finally can get down to this, what is it? What's the value here? 0.5333 code symbols per source symbol as a result of this source extension. And we've already met the requirement when we get that far because we're low enough, but it's also possible to get all the way down to the 0.469 if you keep making more source extensions, is the way you view this. That's what we're supposed to be able to get to based on the entropy. We just have to work harder to create the source extensions. Does that make sense? It becomes more complicated, but you can get the entropy higher, and then you can reduce the flow, the bit rate, because you're playing games like this is doing over here.
Right. 'Cause I guess with the longer code word, you can more closely approximate symbol probability to code word.
I think that's correct. I'm not thinking a lot in those terms, but I think it's along those lines. What you have to do is you have to go look in the book and see that there's a lot more in there. There's Shannon-Fano source coding, and then Huffman source coding. And this is what you were mentioning.
Yeah. One of my classes, I implemented Huffman coding.
Okay. I like it. I'm not as excited about source coding as I am channel coding, because that's just kind of where I've been at with the physical layer. Is what do I need to do to the physical layer? Somebody else takes care of the source coding, but I'm saying that, not saying I don't care about it. It's just that you can't be an expert at everything, and I'd rather just assume somebody else knows what's best for that. Like, for the longest time, when I first started doing screencasts and stuff, I was using Apple's, what was the file scheme that, I probably don't have it on my page anymore. It was in here though at one time. I switched to MP4 from Apple. What was their?
AAC or something.
Well, AAC is for audio.
Yeah, I don't remember their video.
It was one of their first video things, and that's just what I used. I was not using a Macintosh computer, but it was just available to me in some software I was using. I don't know if any of you remember because you're younger than me, but it existed, and I just took that for granted. And then when MP4s became available, I thought that was the better way to go, and it was more compression but higher quality. And I was after both, actually, I think. Or at least I think that's what it was. Did any of you know? It was QuickTime, that's what it was called, Apple QuickTime.
Right.
I don't know what's inside that, but I believe MP4 is both better compression and higher quality.
I think so.
You believe so? I'm pretty sure it's true, but I mean, why do we go to any new technology standards? Is because we're getting something, and we have to get those two, some of those two, if otherwise I'm not interested in it. I mean, of course, the other thing was, and the other reason why you say, why does it take so long for me to put up a video? This, of the two lectures I give, this screen is quad resolution compared to what I do in the other classroom. So I'm capturing it at the full quad resolution right now, and when I produce this video to compress it down to an MP4 at 1/4 the resolution, it takes considerably longer. It's not 4 times as long, but it takes, I don't know, maybe a couple of hours beyond it. It takes more than 3 hours to compress down the hour and a half or whatever, almost 3 hours that I'm doing in here. It takes at least as many hours as I'm recording, but it takes even longer for this one because it's bigger. So that's another factor. Only in production though, but if it's live streaming, then you have to do that on the fly, and my son does live streaming at our church for church services, and he does the compression right there in his video encoder box, and then sets it into YouTube and Facebook, and then they have to, you know, suck it up. When I say suck it up, I mean they have to be able to manage that pipe of bits so that the video can stream live. And that box that he has is kind of the key to allowing it to happen. I don't have any such thing on this PC. It's just recording it as raw, and then it gets compressed later. Okay, so next theorem. This is, now we're moving into channel coding. So this is what the rest of the lecture will be on today, channel coding. Fundamental theorem says, given a discrete memoryless source, each symbol is perturbed by noise. That's been our additive white Gaussian noise, or perhaps channel fading, intersymbol interference, multipath. So we have a capacity associated with the channel and a source with positive rate R. If R is less than C, there exists a code such that the output of the source can be transmitted over the channel with an arbitrary small probability of error. So the channel capacity is going to be measured in terms of the signal to noise ratio that's available in the channel. And then the idea is if we've got R less than the channel capacity, then we can create a code that can drive the error probability down as small as possible. And that's the miracle of coding theory. So our fundamental law that we're going to use that came along in combination with Shannon and Hartley is called the Shannon-Hartley law, and it says for an additive white Gaussian noise channel, the channel capacity, and that's what the C is B, the bandwidth occupied by the information in the channel, times log base 2 of 1 plus signal power over noise power. And this establishes the trade-off between channel capacity and signal to noise ratio. So this is very fundamental, and there's a little derivation now here in the book and in the notes, which then leads to this fundamental limit that comes about for channel coding. So we can first go through some conversions because we'd rather have it in terms of EB rather than signal power. So we go back to the binary antipodal, and we had EB was S times TB, and then the bit rate RB is equal to 1 over TB, and that's going to be the channel bit rate in bits per second. So channel capacity will fit into this through this equality, and then we can, pardon me?
Sorry. When you say RB equals CC, that's only for binary coding.
Yeah, that's right. So we have EB is S over CC, and those are two quantities that we have in here. So we're trying to make some substitutions. Then the noise power is N0 times B, and this is assuming a single-sided noise power spectral or single-sided bandwidth B. So N0 is the single-sided noise power bandwidth. N0 over 2 would be the two-sided. So we can replace S over N by EB over N naught and CC over B. So now we have all the quantities that we're wanting to get into place. Put that back into the Shannon-Hartley law, and then solve for EB over N naught. This seems a little bit awkward, but it's what the books do to arrive at this Shannon limit, which is a pretty important number. So raise both sides to a power of 2. So we have, when rearranging things now, you just have to, I'll just say visualize. What I'm doing, I'm just doing the algebra on that, right? So I'm just going to raise to the power of 2, 2 to the CC over B, and then what I'll have on the right-hand side up above is 1 plus the EB over N naught CC over B, and then I subtract that in the parentheses there, and then I bring across B over CC, and then I have EB over N naught isolated. And that's now into the form that we can finally make some approximation. So we're going to assume for our type of modulation scheme, we're going to assume that the bandwidth B is much greater than the channel capacity, and then approximate the
Why is that a valid assumption to make, or when is that a valid assumption?
When the available bandwidth is large, I think is the way of looking at it. Bandwidth is large, channel capacity. So I'm thinking of, and we're going to see this in a moment, when we have a scheme like FSK, remember FSK just consumed massive amounts of bandwidth, and that's kind of the situation here. But there's other scenarios where this still is valid. So this is going to just drive a limit in this from the Shannon-Hartley law and provide the channel coding limit. So we're going to approximate now the 2 to the CC over B using this binomial expansion for e to the x. Now, if you're like me and had never seen this before, I'd say we don't have any natural log or any e showing up in here anywhere, but you can take anything, any log, and write it in terms of the natural log, right? So it's just going to be the conversion that he's going to go through. So e to the x is e to the x for CC over B being the exponent being small is approximately 1 plus x. That's just the first degree polynomial representation for e to the x, and then put that substitution inside of here, and so that's where that's coming from. up there. So we have the natural log of 2 that comes out of that, and so we get this expression, and then finally in the next line, so we have that, and then the next line, we can then rewrite EB over N naught as approximately under this assumption of B much greater than CC. Things kind of collapse down, those go away. So it becomes natural log of 2, which seems very uninteresting, which if you put that in terms of dB, that's minus 1.6 dB. You know, it's 10 log base 10 of natural log of 2 is minus 1.6 dB. And that becomes the Shannon limit for EB over N naught on a channel, minus 1.6 dB. So as B grows without bound, EB over N naught can drop all the way down to minus 1.6 dB, and we can have reliable communication. We haven't seen that in anything up to this point, right? We've always been, I mean, just a figure of merit is around 10 to the minus 6th error probability was corresponded about 10.6 dB on BPSK. So now we're saying we can go all the way over from 10.6 all the way over to minus 1.6 and get reliable communication of an arbitrarily small error probability. That's amazing, right? Maybe it doesn't seem amazing, but to me it does. So if you plot it just as the EB over N naught curve from the Shannon-Hartley law, and then you look at this asymptote, which we've just been exploring. So what we've been exploring is this part, just because we wanted to see what the limiting argument is. As RB over B, the bit rate over the bandwidth, and this is, you know, lots of bandwidth is in use here, but we can obtain this minus 1.6 dB channel coding limit. So that's good. Not good. I mean, we're not going to be able to operate on that side of the curve. We're going to have to operate on the RB less than channel capacity side. But the hope, intent would be that you can find schemes for communicating over a channel that can be just on the upper side of that curve. And that's what people have been in search of. It's the holy grail of coding theory. Can we find a modulation scheme combined with some coding scheme that together can get us very close to that curve? And it turns out LDPC helps a lot in that as one particular example, but this next page is what I've been talking about since 2 chapters ago. This came out of a book that I used to have. Somehow or another it disappeared. I don't know. I lost it somehow or another. The book, Digital Communications, Fundamentals of Application, came out in 2001. This was originally in a magazine article of the IEEE Communications Society has a magazine that comes out, I think, once a month. Communications Magazine, I think is what it's called. And it generally has nice articles, easy reading articles about advances in communications theory. So this article was one that I originally saw in that magazine, but when I had my information theory coding class, this article had been out for a while, and we talked about it, and then I decided to put it in my notes. So you can see, if you look closely, you can see print from the back side of the page on there when I scanned it on the scanner, because I didn't have an electronic version of it. So I just think it's a nice curve. So you can see different modulation schemes we've already looked at. This just plots that Shannon limit differently. It has, for negative SNR values, it has a scale change, and then for positive EB over N naught values, it has a coarser or bigger step size on in dB. And so what we see on here is modulation schemes we've already looked at. I mean, like, as an example, you know, this one is 256 QAM. Here we can see our QPSK and BPSK. And then for the really high order MFSK, like this one, they're all in there. They're not super fantastic. I mean, I guess, I don't know, if I look at the distance, and how you measure distance, of course, is subject to your interpretation. In this case, the error probability is 10 to the minus fifth for all of those points. So that's small, but to talk about arbitrarily small means you actually have to pull further away from the curve to operate at a higher EB over N naught. But I don't know if that's going to be sticking in your memory or not, but to me it does. It just says 256 QAM up there is pretty close to the limit. QPSK is not too bad either. BPSK is not quite as good. And then if you want to operate at low EB over N naught values, you can go with high order Emery FSK, which are that M is equal to 16 at the bottom. And then there's furthermore representations on the right side of the curve as power limited. Bandwidth goes really large, but you're power limited if you want to use one of the schemes down below, and you're bandwidth limited using schemes up above. And BPSK is just sort of right there in the middle of the whole thing. It's not great. So, but now if you add in channel coding, this is without any channel coding, so you haven't put channel coding on this yet. This is just the raw unencoded and decoded over the channel, but this is just how these schemes stack up with respect to information theory and the Shannon limit. So with channel coding, we can push all of those points closer to the limit. Does that make sense? How? Don't know yet, but you can do it.
Would CRC be an example of channel coding?
Yeah. But CRC doesn't correct any errors, does it? It just simply lets you know.
CRC, there's like, you can do corrections within some Hamming distance or
Hamming distance?
Hamming distance.
Yeah, we're going to talk about Hamming distance here next, actually.
So I know the word, I don't really know what it
Yeah.
is, but CRC can do small corrections, I think.
So I could say on here, so with coding, you can move left, ultimately. But you have to be really careful, because the tendency will be that you will have to increase the bandwidth to encode, and then the source rate's going to have to go up when you encode. So you might get closer horizontally, but you're going to get worse vertically. So, but that's an amazing part about coding theory. You can actually beat that out. So the curves up above answer this bullet. They say through the design of the modulation scheme by itself, we can get some options. We've been talking about that for the last two chapters. And then what we're talking about now or next is forward error correction, is to try to design a code that can actually get us closer. And then there's no bullet down here, but this was what I mentioned earlier, combined modulation. Encoding. Two basic classes of codes are block codes and convolutional codes. So those are the two that we're going to look at. I'm no expert in either of them. I'm less of an expert in block codes, although they seem simpler to me. I've been more fascinated over the years with convolutional codes, only because in my dissertation I had to learn about how to implement a Viterbi algorithm for maximum likelihood sequence estimation, and I first learned about Viterbi algorithms when I studied convolutional codes in my coding theory class. So that forced me to really try to understand convolutional decoding and then be able to take the same Viterbi algorithm and use it in a different fashion for maximum likelihood sequence estimation. Whereas block codes just seem to be more linear algebra oriented and more classical, I think, too. So this is the definition of a block code, generic block code. It says that you group the serial source symbols into k symbol blocks, and then you have n minus k check symbols to make code words. The length of n is greater than k, and then the code is referred to as a nk code. So n symbols in the block, and k of them are source symbols. The other way of giving a measure of the code is the code rate, and that's k over n. So what we want to do in all cases where code rate is talked about is you want to make that number as close to 1 as possible. You know, we'll have, say, a rate 1/2 code, and a rate 1/2 code means n is twice k. So that means for every source bit, we put out 2 code bits, and that's pretty inefficient. I mean, if you're doing a serial bit stream, like if you're doing BPSK and you had a rate 1/2 code and you wanted to send 1 megabit per second of source bits, you'd have to put 2 megabits per second of channel bits through in order to offer up the 2 to 1, right? And that's, if you don't do anything with modulation, that's saying that your BPSK is now going to occupy twice the bandwidth, because it's going to be pumping away at 2 megabits per second on the channel to get 1 megabit of source information through. Sounds frustrating, doesn't it? It's like, I want to do better, but I have to pay something for it. And but see, there's other tricks that can be done. So that's,
So you send a total of n bits.
yes.
Right.
And with blocks, it's done like this. A long block, like LDPC, has very long block sizes, but it has this sparse matrix that we're going to see eventually. But
Yeah.
whereas convolutional coding is done in a convolution-like fashion with XORs and shift register, and it is always pushing out for every new bit that comes in, it will push out so many code bits.
Right.
And then it just, as another bit streams in, 2 more come out. And the standard way is 1 comes in, 2 come out of this encoder, and then they just get turned like this, and then they march out, 2 for that 1, and then the next 2 from the next one. Whereas blocks are grouping things in a different fashion.
Then in hardware we have code called gearboxes, which handle the rate mismatch between input and output, and it's a bit involved.
In your ASIC or whatever.
Because you need to handle the unequal rates on either side.
Which is kind of like DSP, where you have rate changing going on.
Yeah, exactly.
Okay, the check symbols that are added in there in the case of block coding allow for correction, or I think, like I was saying, and if I'm remembering right, for the CRC, at least detection of errors, because isn't the purpose of the fundamental initial purpose of a cyclic redundancy check code was to just see, are these bits that I just got is there a chance that they're wrong? And if they're wrong, then you ask for a retransmission. Isn't that what the fundamental
Yeah.
CRC idea is?
And yeah, there's some extension that can do small corrections, and if not, ask for a retransmission.
Right.
But yeah.
Our desire is to achieve error correcting with a code rate as close to 1 as possible. So it's like we don't want anything to be easy, we want it to be hard. It's like get something almost for nothing. And all of these, these schemes, there's a lot of different things that people have played with. So Hamming distance refers to a geometric view of how code words are assembled and how you can discern whether or not there's an error and whether or not you were able to correct an error. So the Hamming distance between two code words is the number of positions where bits differ. So it's just a weighting called the Hamming weight that counts the number of ones where the code words differ, because XOR always returns a 0 if they're the same, and it returns a 1 if the two bits are different, right? That's the essence of exclusive ORing. So, and then the geometry says if two code words are distance 5 apart, then you're able to correct. It's going to be, if they're 3 apart, then you can correct 1 error. I guess is one example. But it's in general, if DM is 5, then you can correct 2. If DM is 3, you can correct 1. So you can't be at a tie-breaking point, because the tie-breaking point is not good enough to get it correct. You have to be firmly on one side or the other, and that's why the error correcting capability is measured this way, dm minus 1 over 2. So 5 minus 1 divided by 2 is 2. 3 minus 1 divided by 2 is 1, so you can correct 1 error. And this is just a picture that Dr. Ziemer has in the book, which says how you can resolve things with a Hamming distance. And then you have the parity checking codes to resolve that. So here's this, I think this is the CRC, although I don't have it written down like this. Detect errors when one check symbol is added. So this is a rate k over k plus 1. And I think that's parity check, isn't it? Just one added bit? I mean, I don't.
Yep.
So that's the essence of this. Parity check symbol is added. So we don't have the capability with one single extra bit to be able to correct anything, but we can at least detect. Then there's another, in leading up to how to design codes, because this is what people have spent their life doing. There's another type of code that I've explored in Comm Systems 1. I used to do this in a simulation problem called repetition code. A repetition code is about as simple as it gets. It just says send the message multiple times. So repeated n times. So for every bit in the source, you repeat it n times in the channel. And so if you have a repetition of 3, then you can correct 1 error. And this is just a picture of how that would work with the repetition coding and how you could correct 1 error. Then this is the probability bit error that can be worked out from the binomial expansion for the binary symmetric channel. Let's see. So the channel rate is n times the source rate. So the repetition code is pretty ugly in terms of efficiency. The bandwidth expansion is just phenomenal because we're going to now have to multiply the bit rate by n in the channel. However, if we have we have an exponential relationship between PE and EB over N naught, we can't overcome that with the repetition coding. But if we have an algebraic error probability relationship relative to EB over N naught, which we did see in chapter 5 of the notes, then this is pretty much like diversity combining for a Rayleigh fading channel. So repetition coding, although maybe not done deliberately, can be viewed that way in a diversity combining channel. And this gets into a simple multiple antenna situation where you'd have, say n antennas at the receiver to get n different copies, and then be able to weight, that's essentially this repetition coding. When you receive it at this receiver, you get your take on what it is, next receiver, the next receiver, and then you vote based on the maximum. The 2 out of 3 see this as a 1, and 1 saw it as a 0. So there was an error on one of the receivers, but the majority voted as 1, and that's the ability to correct for an error. But that's in the physical channel environment. But it is, I just put this bullet in here because I was trained on this. Dr. Zemer basically said, wait a minute, it is a bad scheme to use intentionally, but in diversity combining is actually a physical channel means to improve performance, and it's equivalent to repetition coding. So does that make sense? You can still think of it as repetition coding, but it's being done in the physical channel. So I think that's actually pretty nice. So what about parity check for single errors? So the idea is to strike a balance between error correction and maintaining a high information rate, which means code rate close to 1. So we can now go into these parity check errors, and this is probably what you're thinking of, Joseph. I'm not tuned into this enough, but it's where we're going to put up multiple parity check bits. So this is exactly, I think, what you were talking about, right?
Yep.
So we have parity check symbols. We have R of them. We have K source symbols. So N is equal to K plus R. And then we can write out all the equations to see that we get zeros. And then you can write out from that then a parity check matrix, which has the identity matrix extending off of the code word matrix. So that's the definition used in block coding. That's what H is. The code words, and then the parity check part is the identity matrix. So there's a partitioning right down here. And then if you get a particular code word vector, T, that will contain all the source bits, A1 through AK, and then it will contain the parity check bits, C1 through CR. And then when you get R is the receive sequence, you bundle that back up into a vector, and then you're going to pre-multiply that by the matrix H. And if that error vector, which is right here, boldface there means that's a vector. If that has at least one non-zero entry in it, that means at least one error is present. And then how do you find out where that error is present?
Are you doing this multiplication? Are you doing XORs or what?
It's XORs, yeah. Everything at this point is XORs.
So you do an XOR row by column.
Mm-hmm. I think it's just two's complement. I mean, not two's complement, but what's that called again? I think of the right word for that. It's mind is drawing a blank on that. It's where you're doing, you're not doing,
Finite fields.
yeah, finite fields, Galeos fields or Galeos fields,
What I
arithmetic.
mean is, when you do this kind of operation, the row onto column, you're doing ands and then you're XORing down, or what?
Yeah.
What is that operation?
Well, I think the safe way to actually do this, now that I'm thinking back to it, is you can convert, if you convert everything to plus and minus ones, then you can do it as standard math, and then you can do the
Right.
additions with converting back to logic. But it has to all be 0 and 1 in the end, though.
Right. Okay.
So then you finally get down to R is T XORed with E, and E is the error pattern. So T is the original code vector that was sent out, and E is the error pattern. They get exclusive OR together, and that's what puts the ones into that H times R. So when we go H times R, we're getting the syndrome. And from the syndrome is where you're able to, because H times E is, not equal to 0, that's where you can determine the place of the error. So that's a property of this coding scheme where that 1 occurs, that's telling you the row of E tells you where the error occurs. And an example of that is the best way to look at this. So we could take this is the H matrix. We can see it's partitioned again. Gotta get my letters right in here.
Sorry, so
N is 6, so the rate of this thing is 3 over 6, which is 1/2. And it can correct one error.
why can it correct one error?
Because of the Hamming distance being, if we go through this, the Hamming distance is 3 between nearest neighbor code words.
Oh, right.
I believe that's the case. Between the nearest neighbors. Like I said, I'm not an expert on this. I'm just sort of fumbling my way along through this. Then I'm going to show you what the Python code does. So we take a received code word which has got an error in it. And I guess, where is the error? I don't remember. I think this example may have started somewhere else in the notes or in the book, but this does have an error in it. So we form H times R, and then we're getting, this is where I'm confused now. Syndrome is column 3. So what am I not seeing here that I'm supposed to see? This is where I'm drawing a blank right now, because I'm looking at this result, and I'm seeing 0, 1, 1, and
Yeah, it seems like 2 errors.
yeah, that's what I'm saying too. But I'm thinking, oh, I know what it is. Okay. That's matching that column, and so I know that that's where my error occurred. So I just simply know that's where my error occurred. So I flip that back from a 1 to a 0. That's what it is. If it seems like magic, it's what it is. That column that we get out of the syndrome tells us which column of the code word portion of the H matrix doesn't match, and it matches the third one. And so that says the third bit is the one that got flipped, so we flip it back again. And now we're back to what we transmitted. So we corrected an error. Not very impressive. So Hamming came along and he developed Hamming codes in 1950. And here's his rules for creating Hamming codes. And I'm just simply listing them. And then you have a parity check matrix that's dimension 2 to the nk minus 1 by n minus k. So that's the parity check matrix. And then the ith column of the matrix H is made the binary representation of I, making the syndrome for a single error the binary representation of the position in the error. And that's just like what we were doing up here. We find the column that it matches, and then that's the position in the code word that has the error in it, and then you fix it.
Sorry, going back, so that can only correct one error then?
Yeah.
Because you'll either get all zeros, which means no error, or you'll get something which will indicate one of your bit positions is wrong.
Yeah.
Because H needs to then have every combination of non-zeros as its columns.
Yeah, that's right. So this is weak. It only can correct one error in this setup.
And that's going to be 2 to 1 and can only correct one error.
Yeah.
That seems not very good.
It's not very good. It's a Hamming code, though. It's like the beginning of all this stuff. So there's an example in the book, a Hamming 7.4 code, which is a little bit bigger. I mean, this is actually, let's see, Hamming 7.4 code. R is equal to 4, so this one, the code rate, is 3 over 7. So this is even worse than 1/2. It's less than 1/2 in this particular case for this code. But let's just take a look at, and then we'll take a break. So what my student did, well, let me just go back a little bit further. So you can see in the read the docs for CycDSP-Com, I've got to work with my co-developer. There's a module that's not listed in here, and that is FEC block. So FEC block is not listed in here, although it is in the package. So if I was to go module index, it doesn't show up there either, but it is in here. So let me just go over and look. Jupyter Notebook examples. I found this the other day. Yeah, there it is. So in terms of Jupyter Notebook examples, he did get this put in. The history of how this came into being is a student did this for me for a 3-credit independent study on open source software engineering, as I called it. So I've allowed students to take an independent study where they're going to add some functionality to CycDSP-Com, kind of like you might do if you were on a development team, and they get credit for it. Some companies might even give employees pay for helping in an open source project. So that was the idea of it. I got the course approved on that basis that I could do something like that, because it is a function in industry these days that people contribute to open source projects in
Yep.
a community fashion. So he developed this stuff for me, and then he delivered some Jupyter notebooks, and he delivered a module of Python code. We examined it. The other two authors of the package examined it, and then it got pushed into it. And then we didn't change the table of contents, apparently. I mean, I lost track of that fact. But this Jupyter notebook that's right here was his submission. So he actually put some figures in from Dr. Ziemer's book. Not sure if that's totally good, but I think he gives credit in here. And he goes through some of the same examples with the matrices. What I did is, because I don't think I have this. This is in here with the figures, whereas the version that I have over here just has the basic code examples. It doesn't have the added pictures, but you have the book. So he got from the Ziemer and Peterson Spread Spectrum book, has a nice section on coding theory in there, block codes and convolutional codes. He's got his module such that you can pick these different J values that correspond to see, where is it? I'm not losing my mind, I'm just losing track of where this was. Hamming code J. Now I guess he used a different symbol. This is what Ziemer and Tranter uses, but J is something that shows up in the Ziemer and Peterson book. So K is the same K we've been using for source bits, and N is the block length. But J is just an index that goes with the Hamming codes from this book. So you can see this table just tells you what the class is available. So when you load up this module, which I've got right here in this notebook, I've loaded up fec_block as block, so I can do block coding. And then you just, when you create an instance of the object called a Hamming code, FEC Hamming, you get that object that you can encode and decode with. That makes sense, right? That's just kind of the way the library works, so you can make use of it. So you put a J value in there like 3, and then that matches the 4 and 7, which is in the notes. And actually, I think I wrote this down wrong over here. It's not as bad as I thought it was. This is 4. So it's slightly better than 1/2. But at any rate, you can put that in here, and then this example, and I have to push this onto the website. You can just look at the attributes of this class, or the instance variables, K, N, and then you can look at H, and then the generator matrix G, which is talked about in the book.
Obviously, then the user needs to synchronize to the block, right?
Yeah, exactly. And he's built that up. He built up a simulation example of that. So here, he just created a simulation in this cell where he's defined. In this case, he went up to an order 5. J is equal to 5. Said he's going to do blocks per frame is going to be 20,000 blocks per frame. So he's going to send 20,000 blocks through in 1-bit error probability loop, counting loop, and then he's going to put a while loop around this so that you are trying to get greater than 100 error events. So you're going to keep sending through this 20,000 block frame, and that's what's going on right here. It's just going to go down, create some random integers to create a frame that's the number of bits per frame, and then with this object, it's not going to work unless I do that. Then I have the encoder method, put in the frame x, and it's going to work its way through that. So x has to be an integer multiple of the code word length. I think that was your question fundamentally. So we're grouping up out of those 20,000. We've got we can divide that by 7 or whatever it is, an integer number of
I'm more
times,
saying like the receiver, yeah, has to synchronize.
onto the start of the frame.
Right.
It has to have frame sync. So this generates it, then we add noise, and we're taking into account a ratio of EB over N naught, and then because of the added coding, we have to throw this ratio in here, this N over K, because we're effectively going to have less energy per bit on the code word side because we're sending at a higher rate. Does that make sense? A higher rate but the same transmit power because we're having to send N bits for every K source bits.
Right.
So that's why we subtract here. So we're lowering the channel EB over N naught. Channel SNR is dB less. And then we're going to, he just does a simple hard decision like BPSK would do, converts it to float, or do a real conversion, add 1 to it, so it's now going to switch between 0 and 1, or 0 and 2, I guess, and then divide it by 2, and now it's back to integers 0 and 1. Then the Hamming decoder takes over, then we count bit errors. So this is each 20,000
I'm gonna
bit
steal
frame.
that idea.
Pardon me?
I should steal that idea.
No, I want you to steal this idea. That's why I'm taking the time to go through this. The while loop is a standard way of doing simulations that run overnight. You log this, and then you get your whole curve. This was just one data point. So what it did was it ran. This is actually built into the sample notebook for the final project. So the same technique, I think, is already in there. Not positive. And then here, it crossed the line. It hit 105, so it stops. It breaks out of the while loop. And then it's got, 105 divided by that, and that's the error probability. So what he did that for several different codes, 3, 4, and 5 J's. And then the way I do this, and the way I recommend you do this for the final project, is you do some sort of a while loop like this. You might harvest a bunch overnight, or just throughout the day you're just writing and running simulations. So when you get a number like this out, you just paste it into an array that's going to be your error probability plot later. You're just sort of tacking it in there and storing it there for safekeeping. If you were to do this in another way, you would write a log file, and then you would read your log file the next morning. That's the safest way. The absolute safest way is if you put this while loop inside of an outer loop that's going to step EB over N naught values, you're going to capture data points with greater than 100 bit errors, and then as soon as that happens, you write that to a file, and then it comes back and it steps another case through. But the idea is you're always writing every new point to a log file, and that way, if something crashes near the end or in the middle, you've got whatever occurred up to that time safely written to a file.
Yeah.
Does that make sense? You got to do, if you don't do this, you'll do it the next time. I've learned the hard way. You can't trust things.
Write to a log on my midterm, and I woke up the next morning and it crashed like 20 minutes in.
Oh, really?
So,
So you already have that hard feeling.
yep. So I appreciate. I'll probably do this
Yeah.
on the final. Now I know.
Well, you got to learn though, right?
Yeah.
I
Yeah, I set
thi-
it to run and left for like 8 hours, and
Yeah.
it crashed 20 minutes in, so it hardly did anything at all.
Yeah, I have that happen a lot too. The story I can tell you is when I was doing my doctorate, we ran on a mainframe system and an IBM system, and the jobs were scheduled across all the people on the campus. When my job would enter, I could monitor and see where my job was in the stack. But once it started running, I was happy. But if it crashed, I still had to wait for it to end. I still had to pick up the pieces and then submit another job. So that's why writing log files became really essential. But the really irritating thing about that was that your job wouldn't even run when you submitted it. It would start running, and then it would timeshare it across all the other jobs. So you'd see that your job was running, but it was being time-shared with other, mostly graduate students, I guess. That was before the days of a PC, though. You can't imagine that, right? But that's the way it was. We did not have, nobody had dedicated computers for doing analytics like this.
Yeah, my mother had to do that for her graduate stuff, and she was like, of course, as soon as you leave your terminal, it's going to crash, but it won't crash when you know.
Yeah, exactly. And that,
Like, the moment you get up, it'll fail.
yeah. So, you know, I'm spoiled. I have extra computers at home, so I will start jobs running on a fairly decent computer. But if I really want to get the best, I'll use my newest and fastest computer and run that one. But when we had graduate students, Dr. Zemer and I, we had a lab space. It's where the battery lab is right now in our building. That was our communications research lab, and we had probably about 5 to 10, you know, PCs. They all had copies of MATLAB on them because that's what we used in the day, and they were assigned. The graduate students were working on the research. The ones closer to the end or working on getting results for papers or something, they had priority. They could start jobs, and it was not very super sophisticated. It was a sign on the computer saying, so-and-so graduate student has got a job running on this computer, do not touch it. And they, somehow or another, they worked out who had priority and how jobs got scheduled to run in that fashion. It doesn't sound ideal, but it's, you know, it's what it was at that time. It's still pretty similar to that, in my view, today. So at any rate, he put all this stuff together after he collected data, and this is what he got for these different Hamming codes. And these are only correcting one bit, but because of the different rates involved, the code rates, you can see how the simplest code is this first one. It's picking up some dB of gain over BPS, uncoded BPSK. But then when you go down to the more sophisticated code, the 3126 code, this is a lot more energy efficient because the code rate is higher, and now you're able to get pretty good coding gain. And if this is at 10 to the minus 6, so look okay? You see the idea there?
Right. Because I guess, yeah, if you're sending extra code bits, those code bits have their own bit error probability.
Yeah.
So smaller codes have some efficiency there, right?
Right, and that's what Hamming, I think, was studying. This is a longer code, but LDPC, low-density parity check codes, take this and drive it to thousands. I mean, it just become huge integers in those two slots for K, or for N and K. Remember, that's what we've got here. Is that right for the Hamming codes? Go back over here again. Yeah, N and K. So K over N is the rate. Okay, there are then many other codes that are out there. There's cyclic block codes. This is a little bit more sophisticated, and this has a cyclic shift of any code word, produces another valid code word, so it allows for some efficiency. In the way you generate the code words, you can do it with a shift register sequence generator, and this is right out of the book. And then you can decode it with a fairly simple technique that's described here. And cyclic codes, some of the popular ones that are cyclic type codes are Golay, BCH codes, Bo, Shahudre, Hakokoingam, I can't pronounce the name, I don't know how to say that name, but, and then Reed-Solomon codes. I know enough to be somewhat dangerous, but Reed-Solomon codes show up for me more often in thinking about them. They show up in like compact disc was designed with Reed-Solomon coating in it to protect the raw bits that come off of the CD. Was a Reed-Solomon code. So Andrew Schmidt, who wrote the code package, wrote cyclic codes in there, and he put in a bit stream to define the shift register that's used in the feedback, and this comes from our textbook, so you can that one can be played with. This is the H matrix for that. And just showing how the object works again. And then he did the same thing here where he ran a simulation, and then this is just cataloging what he got out of it, showing different types of cyclic codes and performance measures. He did not get these to run down as low an error probability. I'm guessing because it was more time consuming on his PC at the time when he was doing this for me. He was a very good master's student. He was like one of the best master's students I've ever had. He was just really, really smart. I mean, smart in all ways, not just one-dimensionally smart. He could write code. He could write C++ code. He could write Python code. He wrote the Pi audio helper with the GUI and the other interrupts and stuff in there, the thread management. I just said, I'd like you to do this. Can you try it? He'd come back in a few days and be like, here's the demo. It's working. It's like, wow. So he got employed here in Colorado Springs and got, a six-figure salary right out of school with his master's degree. Nope. I mean, now that's probably more standard, but he was one of my first students to get that high of a salary, approaching my salary, actually, my 9-month salary. But I suspect he can work as hard as he wants to for the rest of his life, but he's married, and I'm thinking he probably has children now, so things will be different. So these are things that he left on the table when he got done, but I was happy with what he had done. And this happened between the last time I taught this class and now, so I'd never been able to show it until now. So you're the first and probably the only people to ever see it. There's also bounds. So the bounds that were on these curves over here were these dashed lines were created using the bounding curves, and that's what most people will use in modeling with coding theory. They won't run a simulation, but he just wanted to show the tightness between the bounds and the simulation points. And it turns out they're exact for the Hamming codes, or what are called perfect codes. This is an exact expression for going from uncoded to coded error probability in those block codes. But then this is another equation that I put in here that Dr. Ziemer has in the book that's good for all block codes. It's just, it becomes a bound then. It's a tight bound though for most cases. So this is kind of handy. And I'm pretty sure he probably has this in the module. I don't remember, but I'm willing to bet that this is in the module. The FEC_block probably has this equation available already pre-coded for you. And these are just examples from the book, which I don't really need to show. We're going to take a break and try to get through convolutional codes and then talk more about the exam problems. So I'm going to stop this. Get my microphone back on. Okay, we're going to finish up with convolutional codes, and then there's a little discussion at the very end. I think I'm going to do something out of order, though, just because I want to make sure I get through just this high level topic at the very end. So I'm going to go past the convolutional coding and talk just a little bit about LDPC and then combined coding and modulation, since there's just a few comments about that. The low-density parity check codes are now extremely popular. They're extremely universal, and I guess I could say I'm fairly embarrassed that I haven't really drilled into them that much. I played with the ideas and read about them, but it's now found everywhere. I mean, it's used in cellular telephony, it's used in satellite communications, and other products for sure. So it's just a linear block code, but it has a parity check matrix, which is sparse. So that's its main feature. It's a very large parity check matrix because it's just very large integers, but it's sparsely populated. It was originally discovered in 1962, and I added this. This is a new version of this chapter that I pushed up yesterday evening. Robert Gallagher is kind of like one of the big fathers of information theory. There's a nice book that he wrote back in the 60s. And he of all people would be the person, from what I know about him, that would have written on low-density parity check codes. He's a guy that was definitely well ahead of his time in terms of his mathematician skills and would have been investigating things like this. So then it wasn't until 1996, and that's a long span of time, and look how many years that would be, that these two guys, McKay and Neal, rediscovered them and said, oh, these are pretty nice, and went on to show that LDPC codes actually can be very effective. And I was reading out of the book that I gave you a chapter out of earlier. Let's see. Barry, Lee, and Messerschmitt, Digital Communications. Remember the chapter I pushed out on Slack from equalizers. So they've got two nice chapters at the end of that book. That's actually, now that I'm looking at it some more again, it's a really nice book. I brought it in one day. It's a very thick book. It's now very expensive, but it covers a lot of stuff, even though it's dated now, but it's pretty comprehensive. So they point out that they're significant because you can get within a few tenths of a dB of the Shannon limit that we were just talking about earlier, the minus 1.6 dB. And much to my surprise, because it wasn't ever clear to me that that besides getting better performance, in the end, considering how much performance you're getting, the complexity is actually less than other types of codes that get similar performance. So I never really thought that was the case. I thought it was strictly good performance, a lot of hard work to decode. I think it still is a lot of hard work to decode, but compared to other codes, I think that's how they can make that statement, to say that getting similar performance from another type of code takes even more work than LDPC. So LDPC has become kind of like the standard. And I don't really have anything else in here. I could have put in some other details, but this is just a small matrix, a 12 by 6 matrix. But it becomes much, much larger than this, and there are standard LDPC codes now that are in the industry. So all you have to do is Google that, and then I think you'll get to the Wikipedia page for LDPC. We could just simply go. What do you want to pick from? It's all over on here, right? I'm pretty sure there's a nice Wikipedia page. Yeah. And it's the holiday season, so they're asking for donations at Wikipedia, but So my suggestion would be to just go read about it here. I'm trying to see if I can see one of the examples of a typical code. Yeah, so 4680, 64800. I mean, these are the types of numbers you're getting into with LDPC codes. Very, very large block sizes and very sparse matrices. So very powerful, though. Game changing, to say the least. So I want to at least point that out. And then another thing, trellis-coded modulation. It's mentioned briefly in the book. Turbo codes are also mentioned in the book, and I already skipped over that. Turbo codes, I guess I didn't skip over that. That's down below here. It's talked about briefly in the book. Dr. Ziemer had at least one PhD student that did turbo codes. They're finicky. They get extremely high coding gain, but they have thresholding phenomena. So the waterfall curve of a turbo code is like a step function. It comes out and just goes way down. But depending upon how this iterative decoding works, it can have floors in it where it doesn't drop as low as what you'd think. So there's things that I learned from being on his dissertation committee about turbo codes. So I think turbo codes maybe fell out of fashion a little bit in favor of LDPC. It was before LDPC became popular that turbo codes were out there. They're still both very, from an information theory standpoint, very, very powerful, complex too. So something that was around, though, when I did my dissertation was trellis-coded modulation, and it's an example of combined coding and modulation to achieve bandwidth and power efficiency. And this is talked about in the book. It's in a SATCOM standard, and I actually got to work on implementing one of these on one of my subcontracts when I was working for a company, Emergent, here in Colorado Springs. And the scheme I was working on was RAID 1/2 convolutional code combined with an APSK modulator. So because I want to get into convolutional codes, I just want to show you the block diagram. The effective code right here is 2/3, so this is already heading in the right direction because that's greater than 1/2. And the way the encoder works is you have a convolutional encoder for 2 of the 3 bits in the APSK system, and then the 3rd bit just goes straight in to this trellis diagram, which we're going to be talking about. So you get 2 bits in and 3 bits out is what you should just see from the left-hand side. You see you have a shift register that takes in 2 bits, or it takes in 1 bit, and then for each bit in you get the taps there on the shift register. The upper and lower taps give out the coded symbol, and then you have the uncoded symbol that's coming in. But then you have a decoding process which is very efficient with the Viterbi algorithm and then another mechanism, and I don't remember the details. I know I implemented it in code though, and it worked and it did well. I developed it in M code. I think I did it in Octave for this company, and they converted it to C code for their software-defined radio, or C++. But all I wanted to really show here is what you can do uncoded 4 PSK, and then you go with 8 PSK all by itself, and you get one level of performance. But if you go with trellis coding in the 8 PSK, you can pull the curve over considerably. And the really cool thing about this is you don't have to increase the bandwidth, because 8 PSK already has 3 bits per symbol, and now we're just going to dedicate one of those bits to the code part, and the other 2 are the throughput bits. So this is a win-win situation, and that's what that curve is showing you. There's no increase in bit rate required because APSK is 3 bits per symbol. So that's one of the things about combined coding and modulation. What do you think? I think it's wonderful, but and that's the types of things you can do with combined coding and modulation. And guys went off and went crazy with this stuff quite a few years ago, 1987. This guy Ungerbach was one of the big inventors of trellis-coded modulation. So it's combined coding and modulation. So now we want to go back to convolutional codes. So a convolutional code is based on having a shift register and then having taps off the shift register that combine with exclusive OR combiners, the bits that are coming in serially at the input. So in this particular case, you just look at the block diagram here and you can see that you've got 1 bit in and you've got 3 bits out. So you have 3 XOR adders in there, and that's telling you how many bits you're going to get out for each new bit at the input. The convolutional encoder has a state associated with it, and that state is what's contained in the shift register. So it's a state machine, and that's kind of the very nature of a convolutional code. And it's called a convolutional code because it kind of resembles the convolution operation when you have an FIR filter in digital signal processing. You have an input signal stream, and then you have taps with coefficients, for the FIR filter, and then you form the output. So it's a convolution-like operation, only now it's going to be in Galeos field, or GF2, binary arithmetic. Polynomial multiplication is what this operation is doing. And that's a whole another aspect of coding theory we just haven't talked about, is all the polynomial representations that go along with both block codes and convolutional codes. So we're just keeping it simple. So the constraint span is, in my notation, it's capital K, but sometimes it's lowercase k. So you get a rate of 1 over V in this system. V is the number of output bits for the number of input bits. And that's the very nature of a standard convolutional code. It will always input 1 bit and then output some number of bits, say V. But now you can also modify that with a technique known as puncturing, and that you explore in the final problem. Puncturing is where you remove certain selected output symbols from the encoder and just don't send them. And it sounds like it's suicidal to do that, but it's not. You can actually still do pretty well with puncturing. And puncturing is just to try to increase the rate. So now the rate is going to, rather than being 1 over V, it can be K over V, which is, remember, the name of the game is to get a rate closer to 1. So you had a question?
Yeah, so I guess you're always computing V1, V2, V3 in this example.
Yep.
But you might decide, sometimes I'll send out 1 and 2, sometimes I'll send out 1 and 3.
Yeah.
Sometimes I'll send out 2 and 3 or something like that.
Yeah, and you'll see that in the final project. I have what's called the puncturing matrix, which is what people define. And there's all kinds of papers written on puncturing,
I guess I'm wondering what would be the advantage of doing that versus just only computing 2 outputs, or why compute many outputs and select different ones?
Because the math works out that you can get better performance,
Okay.
if you can believe me on that. Plus, with a straight convolutional code, you're going to have, at best, 1 in and 2 out. You can't do anything smaller than that. So that's a rate 1/2, but with puncturing, you can actually bring it up to, say, 7/8 or 3/4 or something like that. So you can get it above the 1/2. And that's the really important thing about puncturing, is you can raise it above 1/2, which means your serial bit rate in the channel doesn't have to simply be doubled. It can be just fractionalized. You know, if it was a rate 3/4 code, it would mean the serial bit rate now has to be 4/3 of the nominal bit rate in the system, which is more manageable. Or if it's 7/8, it would be 8/7 the serial rate. So people in the satellite community were the first ones to really get involved with convolutional coding, and it's just a standard. So this is the rate 1/3 example. Yeah, I forgot to say this example shows V, so there's an arbitrary number of adders, but this is just a rate 1/3 example, and it has, you know, what makes the convolutional code unique is are these interconnects. And those get defined in terms of polynomials. So I'm just going to jump over to what we have well, okay. I need to do this. I don't know if I downloaded it. So I need to do this. I don't remember that I put it on here, so I have to go back over to here and go to the project. Just let the project open up in here. And the very nature of convolutional codes is you get different performances for different values of constraint length k. So they're generally specified. If you go to like the Ziemer and Peterson Introduction to Digital Com book, which is out of print, or other coding theory books that have convolutional codes, they're always specified as octal values. That's just been the history of coding theory. Octal seems weird, you know, base 8, but so in my library, in DSP, Scikit-DSP-Com, it's put in as a polynomial, and the polynomial corresponds to the taps that are in the shift register. So for a constraint length 3 code, the two rate 1/2 code, the two polynomials are 101 and 111, and that's just telling you how the taps come down from the shift register, 1, and then it skips, and then another 1. So those 2 bits coming out of the shift register are XORed together, whereas the other polynomial of 3 1s mean all 3 outputs get XORed together to form the other output. And then you can just see what the other patterns are. You're going to play with, I think, it's k equals 5. Most real systems use constraint length 7 because the performance is very, very good with constraint length 7. So but to discuss how the Viterbi, how the decoder works, we have to look at we have to look at initially a code tree. And the code tree gets you convinced that this is a very messy proposition. But you start off on the left-hand side, they're saying you're going to enter in either a 1 or a 0. So if you enter a 0 in, you go up in the code tree. If you enter a 1 in, you go down in the code tree. And so as you progress through the code tree, you're going to go up or down depending upon what the next bit is coming into the system. So 0 is input first, so you go up, and the output bits corresponding to that are 3 zeros. If you enter a second bit of a 0, which is the next spot up in the tree, you still output 3 zeros, and then you can trace your way through. So you might have a pattern, which is what's highlighted in here. That pattern is 1, 0, 1, 0, and then I guess 0 is indicated there at the end. I'm trying to remember why that is. Yeah, 1, 0, 1, 0. So this is what you fed in, and then what the encoder put out was what's down below each of those branches. It put out 0, 1, or 111, 101, 011, and 010 were the 4 triples of source or channel bits that went out. So actually it's right down here. So you can't just build a code tree to easily decode what was sent, because the number of outputs there is just growing and growing and growing. So it's Viterbi of Qualcomm that invented the algorithm he put his name on, called the Viterbi algorithm, but it's actually dynamic programming. If you were to take a course in operations research, which I did because it was just available at the university I went to, it was just one of many optimization techniques you could learn about. Standard optimization that you're familiar with Hessians, matrices, and gradients, and so on, is one branch of optimization. Another branch of optimization theory would be linear programming, and then yet another branch of optimization theory is dynamic programming, and this falls under dynamic programming, where you're trying to find the shortest path through some structure of operations. And I don't know, does linear programming mean anything to either of you?
I did some dynamic programming in control theory, like Professor Trimboli taught it.
Okay. You did dynamic programming?
Yeah, like in moving through state space and so on.
Okay. Was it dynamic or
Yeah, it's dynamic.
but it wasn't linear programming? Linear programming comes up in economy and other things where you're trying to constrain many variables, and linear programming ends up being a technique for tackling a multivariate optimization problem. But I don't do that. A friend of mine, though, is an operations research guy, and he used linear programming all the time for stuff he was doing. He worked on energy stuff related to power plants and distribution of power and how you make all this stuff optimize out. It's pretty powerful technique. But dynamic programming and then using a trellis is what you can do, is what the Viterbi algorithm does. So the Viterbi algorithm looks at information here, and the states are generally, like for this particular trellis, there's 4 states, and the states are assigned based on the shift register. So, and I've done it either way. It turns out you can do it either way. You can either say these 2 define the states, or you could say these 2 define the states, because in reality you're not tapping off over here, so you have 1 input and then you have 2 states is what it comes down to. So the book says let's use S1 and S2, but I've done it equivalently using S2 and S3. So when you have the states, you're going to say what are the states of those registers, and you've got 4 different values for this particular trellis. So it's always going to be 1 less than the number of shift register elements that will define your states. So we look at the states, and then we look at the input as being a 0 or 1, and then we're looking how it propagates through the rest of the states in the shift register, and then what the outputs are. So from that you can come up with putting all that information on a trellis equivalent to just listing it in the table. So you keep your states here like we talked about, the 4 states, and then if the input is a 0, the current input is a 0.
4 states if there are 2 shift registers. Oh, never mind. Sorry.
There's 2 shift registers. There's 3 shift registers entirely in the block diagram, but one of them is the input, effectively, and then the other one is the 2 stored states. So I know this sounds confusing because I've been bothered by this before too, but
No, never mind.
are you good?
Yeah.
Okay. So there's 4 states, and then the dashed line represents a 0 coming into the trellis, so it's all zeros. But if we took initially a 1 coming in, we put out all 1s, but then then we'd be holding You know, as soon as we put in a 0, this shift register moves over. So as soon as we put in another 0, the old one falls off the end and a new one shows up. So if we put in a 1, which is what we're doing here, we end up right at this state. Because a 1 means after we shift that value in, it's gonna show up over here as a 0, 1. And you can order these in the opposite direction too. You can put the most significant bit or the least significant bit in the state, however you want to do it. It'll all work out in the end. But in this case, we put in a 1, so we transition down to here in the trellis. We put in another 1, and we're going to transition down to here. If we put in a 0, then we'll transition back up, let's see, up to here. And if we put in another 0, we'll eventually transition back up to the starting state. So one of the things you can see about a trellis is it will have a remerge. But the whole point of the trellis in representing how to decode a convolutional code is to be able to search backwards to figure out where the most likely path was that was used to arrive at the current state. So the Viterbi algorithm is, like I said, state-based. It's searching out the maximum likelihood sequence that created this path through the trellis. So when you're finally gone far enough into the trellis, you can finally prune things out by looking at Hamming distances between, there's always, in this case, there's always 2 branches that merge into any state at any given time instant. So the point of the trellis is you have a metric, which is a measure of distance, the maximum likelihood or maximum a priori distance, and you prune it back. So when you arrive at a node, what you'd be doing in the decoding operation is you'd say, if I can get this to work, if that distance was shorter, then this one would come in from here, and you discard the one that was less likely to occur based on this metric or Hamming distance. Or in the case of soft decision decoding, it's minimum Euclidean distance. So there you keep the smallest value. The minimum Euclidean distance is kept as a measure of what was the most likely path it came in on. And when you finally evolve through the trellis a number of states out into the future, called the decision depth, things will be pruned away based on this Hamming metric pruning process or minimum Euclidean distance pruning process. And you'll be able to stand at that node and trace back all the way back so many states. So in this case, you might trace all the way back over to here and say, oh, I know that I must have put in a 0 way back over there to take me down that path. You don't know with high confidence what you just did, what was the bit that was entered in to get to where you're at, but you do know of tracing back with high probability that that's what entered at that point. I know I'm being pretty vague about this because I'm also running out of time, but
Why do you need this probabilistic? Is it because multiple inputs can produce the same output sequence? Or why is
yes.
this needed, I guess?
When you trace everything through the trellis, you get multiple paths through the trellis, but then when you prune it and trace backwards, you see that everything emanates from one branch, and that's what you're looking for. You're wanting to figure out what branch did everything emanate from, and then you can say that must have been a 1 that was sent 5 bits ago in my trellis. So it's the pruning process and trying to optimize the distance, whether it be maximum if it's a Hamming distance or minimum if it's squared Euclidean distance, trying to find the most likely path through the trellis, and that's where the tracing backwards comes into play. So unfortunately, I'm going to have to deal this out by talking to you in Slack or talking to you next Monday, but if we go to my convolutional encoder, which is, maybe this is good enough, that's in here. This is probably good enough in here just to not run the real code right now. this is the full-up trellis in what's called steady state, and there is a homework problem on this. When you finally get into steady state, which we saw, and then there's coding theory. This is the steady state setup in here. When you finally get into steady state, the trellis has, I won't let me do that. It's not going to let me do it. Oh well, I won't argue with the software. But that's the steady state. Those are all the transitions that you can make when the trellis has gotten up into steady state. And if you go over to here, this is just showing you what that steady state trellis does. We created an object, effect, convolve. We gave it these tap weights or these polynomials. We said we're going to make a decision at depth 10. So when we finally get 10 steps in, we're going to stop and we're going to analyze what happened 10 steps back. We're going to be able to determine what was the most likely bit that entered at that point. So put some random, create some 10,000 bits. I'm going to start with the state at 0, 0. That's pretty common, just starting at state 0, 0 in this 4-state setup. And then I put in some noise, and then I put in some a hard decision device here, and then I'm scaling by 7 because I'm having you use the soft decision decoding. So you're going to take the metrics internal to the Viterbi decoder and make them work on a soft scale, and that's talked about in the handout. The soft decoding idea is talked about, well, rats, it's way over here. No.
You said you'll give us some more help with this over Slack.
Yeah, oh, definitely. I mean, if you ask me questions, but we'll talk about it next week too. Trying to think.
Was due when? This next Friday?
What did I say in here? No, it's due Wednesday nominally, but you know, I can give you more time. So if we meet next week, I could push it out further as necessary on the convolutional decoding part. There's examples of everything in this notebook, though, and that's what I kind of wanted to emphasize. I guess the other class, I'm sure, is not going to come in here today. We haven't seen them for a month now, right? But I've got a person I'm giving a quiz to at 11 for my lab class. Be looking it over.
I can do all of the other problems, but
Yeah,
still do it.
yeah. But this, you can just start playing with it. I have everything in here, and if you run an example, like if you, this notebook I haven't initialized because I just started it at break time. Let's just see if it will produce, well, play it safe. I'm going to restart this. Then I go down here, the convolutional encoding. So I have this example in here. And I'm getting these error messages. This is something, or it's a warning message, it's a deprecation. I got to ask my helper about this too, but everything seems to work. I don't know what, it's something in Python that changed. But here I just had to do a picture of the trellis. Here I'm going to put in 10,000 bits. Here I'm going to give a starting state of 0, 0, and then the values have come out of the encoder, and now I'm going to put noise on them, and then Viterbi decode them, which is what I just did. And after I get done decoding, this is the XOR of what went in and what came out, and it's all zeros, meaning that it's error-free. And then if I want to do an error probability counting over the entire record, I can see how many bits were received and how many bit errors. Something I've done in this notebook that I've never shown you before, but I'm now doing this. My assistant, again, added this capability into scikit-DSP called the logging module that's in the standard library Python. So I've turned logging on so it will log outputs. These outputs used to come automatically, but when he implemented logging, they don't show up unless you turn logging on. So I've turned logging on. So anything you see down in the end here, don't be overly alarmed at it, because this is just telling me that Digital Comm is sending a log message out for the bit error tester. The bit errors function is what's logging, and it's just telling you the alignment tau max between the two bit streams, and correlation max occurs at index 0. But so there that is, and then this gives you an idea of how the pruning in the trellis is going. This is 9 steps back from 0, so when we take our 4 states, this is taking the state diagram, but I've got negative values rather than positive so that it can be oriented properly. But these are the traces back through the trellis, so it's rock solid over here. Everything is emanating from this same branch. And to show you what I mean by that, suppose I take the signal to noise ratio. Right now it's at 2 dB. Make sure I get this right. ES over N0, yeah, 1 bit per symbol. So if I take this down to 0 dB and run it again, I think I will get some bit errors, but maybe not, because I got 92-bit errors. Here the traceback is still looking good though.
Sorry, so when we're looking at that trellis, can you scroll down a bit?
Yeah.
It's saying, if I'm reading this correctly, it's kind of saying from -1 to -9, it
Every
feels very
branch.
confident that that's what it must be.
Yes,
And
exactly.
then and this transition from -1 to 0, it's saying, I'm not sure, I might have gotten a 1.
Yeah, because I haven't traced back very far. What happens in a normal scenario though, and this plot is just not working out the way I thought it would. Let me take this back to 1 dB, signal to noise ratio, and then I'll run the decoder on that. No bit errors in there. It's saying I have 18-bit errors. I'm not sure I believe that or not, but what starts to happen though is that this non-alignment gradually traces back further and further. I see in inconsistency. It takes longer and longer for it to coalesce as emanating from the same branch. But see, any branch that it emanates from, it can be a 1 or a 0 depending upon the sign in the trellis, right? So that is not good enough to say what was sent. It's the sign. So it could be the one at 0, it could be the one at 1, -2, or -3. They would all carry the same bit might be decoded out of that, but it's the fact that we've waited long enough with the pruning operation in the trellis decoding to have it emanate from a point of coalescence like that. So we're highly confident. If the decision depth is made shorter, then we're more likely to make an error. And like I said, let me try another value here, -2, and just see what that does. Because I'm seeing a lot of bit errors, and I'm not really sure that this block of code is working correctly. But let me just try this again. There, it's more confused, but it's still very solid way back over there. So it says there's 18-bit errors out of 9,991. When you decode with convolutional codes, though, errors tend to occur in bursts, because we saw in the trellis how it remerges again after so many bits, and that leads it to making errors during that. If it gets off track, then it will make a lot of errors, and then it finds its way back again, and then it does good. So the nature of bursty decoding like this means you have to get more than 100 error events, because 100 error events tends to not be as good for convolutional decoding because things occur in bursts. So you can start with 100, but I don't remember what I did in here. I'm pretty sure I gave you sample code down here with the while loop. Yeah, I did run these with 100 though. So this was the code we were looking at earlier for convolutional codes. Okay, sorry for all that falderall. I should have not gone into block coding.